My name is Erica Marie Hartmann. I am an assistant professor in civil and environmental engineering here at Northwestern University.
We're really interested in seeing, what's out there in the world. Mm-hmm. So we go and we collect stuff from different environments, from different rooms, from different buildings, from different places, and we see sort of what's going on in there. And then one of the things that I'm really interested in is seeing maybe how we can use these bacteria to accomplish certain things.
It's covered, don't worry. You got it.
Woo, first try.
Woohoo!
This is where all the magic happens.
Mm-hmm.
This is where, like if you're growing bacteria, we'll count the bacteria. So we've got all these plates with bacteria growing on them.
What type of bacteria are we growing in here?
All kinds. So I think most of these at the moment came originally from indoor dust. Mm-hmm. So just like the dust bunnies in the corner of the room. But we also have some that came from toothbrushes. We have some that came from hospitals. We have, I think what else we have at the moment? All kinds of places. Because, basically wherever you can think of, there are bacteria growing there. And so we just want to know who's there. So one of the things that we're really interested in is antibiotic resistance. So once we've grown these bacteria, we then ask if they are capable of also growing in the presence of an antibiotic. So that's one thing that we check. An antibiotic or maybe a cleaning product or something else. One of the things we're really interested in is paint. And so what Jinglin has done here is she's got bacteria growing all over this surface. And then she takes a little sheet of drywall that she's cut and painted, which is different paints, and puts it in contact with the bacteria. And you can see there's actually a little zone here where the bacteria can't grow. And that's because there's something in the paint that inhibits growth. And the bigger that zone is, the more toxic it is to the bacteria. Yeah, so that's a cool thing.
So paint is safe? You can eat paint?
No, don't eat paint. You're probably better off eating the bacteria. It looks like Adam is aliquoting something.
DNA extractions.
DNA extractions.
Many DNA extractions.
Yeah. Here, we'll go in here. We'll leave Adam alone. Adam's busy.
In the zone.
AutoZone? I'm sorry, I'll leave now.
This is the clean side of the lab.
Okay.
So this is where we work with DNA. So for example, we don't have anything in here, unfortunately, for me to show you. But if you're doing a DNA extraction and you want to make sure it stays super clean, especially because, for example, if we're working with microbes that come from dust, but there's dust all around us, how do you know that the microbe that you're working with in your sample is the thing from your sample versus the thing from the dust all around us? So this is a biosafety cabinet that right now is UV sterilizing itself. So there's a UV light on and the whole thing is sealed. So all of the DNA that's in here is being destroyed. And lift this sash and work in it, and the way the air flows, it keeps anything from falling into your sample while you're working on it.
Oh, okay.
So it stays super clean.
Cool.
And we actually have a whole room that works like that.
Do you float?
It doesn't, it only works for microorganisms, not macroorganisms.
Cool.
So this is our robot room. This is Osimo, the robot.
Nice to meet you.
If you look at the air system in the ceiling, the way we designed it, it's getting circulated up. There's a HEPA filter up there. So this room stays super clean. And so basically you can set up whatever you're working on. Like, for example, the way Adam is pipetting over there. You can have Osimo do all the pipetting and basically close the lid and then make sure the air is circulating in such a way that nothing falls in your samples. It all stays super clean. So we get the microbes from the dust and we grow them in the other room. And then we can extract the DNA from them. And then, like what Adam was doing, he was aliquoting the DNA. And then we can amplify specific pieces of the DNA. So for example, let's say we find some bugs that are really good at growing on paint and other ones that aren't. We can look for specific genes that they have, and we can amplify those genes or detect those genes using PCR, which is what's going on here. So the end purpose is having a better understanding of the world around us and the impacts that we have when we make certain choices about the kinds of products that we use indoors. So let's say you found out that a certain kind of paint maybe would get rid of some bacteria but not others, and it turns out that the bacteria it gets rid of would actually make you healthy. So then we can decide, oh, maybe we want to keep those bacteria, so we're not going to use this paint. That kind of thing, so that we can make better informed choices about the kinds of chemicals that we use in our buildings to make sure that we have healthy indoor environments.
And we're not like building up
Antibiotic resistance, pathogens, all of the things that we don't like.
cool.
Yeah.
And we don't have a mega outbreak on our hands.
Hopefully.